This video we are going to discuss surface area of solid of revolution. Surface area of solid of revolution. Just like how we found the arc length, how we found the volume of the solid, in the same way we're going to dissect our solid into very thin bands, find the surface area of each band, and then integrate them over the range of x values or the y values. Surface area of solid of revolution. So remember from the previous section, arc length formula. Arc length L is integral of a to b square root 1 plus f prime of x squared dx. Now imagine our solid is formed by rotating the curve f of x along the x-axis. So we rotated the curve f of x along x-axis and we came up with this solid of revolution. We're trying to find the surface area of this solid of revolution. It's made up of curved surfaces. So there's no geometrical formula, no geometry formula that will help us find the surface area. Instead, we will be using calculus. We're going to divide our solid into thin bands. So I did draw one purple band on the side here. If I open up the band and straighten it out, it would look like a rectangle. The height of the rectangle or the width of the rectangle would be same as the arc length. So this little piece would be the arc length. Height or width of the rectangle would be the arc length. And the length of the rectangle, imagine if you open up, your solid was formed when you revolved 360 degrees around your axis. So the length of the rectangle would be 2 pi r, 2 times pi times the radius, 2 pi r. Circumference of that circle would be the length of the rectangle. So surface area of one thin band is going to equal 2 pi times the radius of the band times the arc length. And we just wrote down the formula for the arc length. It is here. And surface area of entire solid, we would integrate the solid over the range of values from a to b, 2 pi times f of x, which is the radius of the solid, times the arc length, square root of 1 plus f prime of x squared dx. Okay, let's look at a couple of examples. Here we have surface area of solid of revolution. Case 1, when we are revolving about the x-axis. So imagine your solid is being formed by revolving about the x-axis. So we are revolving about the x-axis, and this is the band we're talking about. If we straighten this band, the length of this band or the height of this band would be the arc length, and the pink side of the band or the length of the band would be 2 times pi times the radius, because it's a circular region. If you open it up, the circumference will be the length of the rectangle. Okay, 2 times pi times radius. Radius at any given point is the height, the y value at that point. So 2 pi times the radius, surface area is the 2 pi r times arc length. We just saw that on the previous screen, 2 pi r times arc length. So 2 pi, the radius is f of x, and the arc length is square root 1 plus f prime of x squared dx, integrating over a to b. If I was revolving this solid about the y-axis, then things would be slightly different. I would still be using arc length as the width of the rectangle, but the radius in that case will be the x value at that point. So instead of using f of x as a radius, we will be using f of x as a radius. Okay, nothing else will change. So for both of these cases, we were given y as a function of x. Okay. So again, to summarize, if y is a function of x, then surface area is 2 pi integral of a to b f of x square root of 1 plus f prime of x squared dx. F of x is the distance between the graph of f and axis of revolution. Okay, if x is a function of y, then the integral would be 2 pi x square root of 1 plus g prime of y squared dy, and the bounds of integration will be the y values as well. Okay, let's look at a few examples. Find the area of surface of revolution formed by revolving the graph f of x equals x to the third on the interval 0 to 1 about x-axis. Okay, there's no need to graph the curve, but graphing might help a little. So this is the kind of curve we are talking about, and we are revolving it about x-axis. So this is how my solid will look like, and I'm gonna cut it into thin bands. If I open this band up, then the height of this band is going to be the arc length L, and the length of the rectangle would be 2 times pi times the radius. Radius for this curve at any given point will be the y value. We want it in terms of x. So surface area is going to equal, going from 0 to 1, 2 pi. The radius is the f of x, which is x cubed, square root of 1 plus f prime of x squared. If f of x is x to the third, f prime of x is 3x squared, which turns out to be 3x squared to the second power dx. So surface area of the solid is 0 to 1, 2 pi x to the third, 1 plus 9x to the fourth dx. This problem looks like a good candidate for u substitution. So I'm going to let 1 plus 9x to the fourth be the u, and 36x to the third dx be du. And I can say x cubed dx be 1 over 36 du. When x is 0, u would be 1. We're going to write this integral in terms of u integral. Okay, when x is 0, u is 1. When x is 9, u would be 10. And I can pull the 2 pi outside. So we have x cubed dx is 1 over 36 du, and we have square root of u here. Okay, pull out the 36 as well, from 1 to 9, square root of u du, which is pi over 18. Square root of u integral is u to the power 3 over 2 times 2/3, going from 1 to 9. 1 to 10. The bounds are 1 to 10. Okay, 1 to 10. Sorry, my eraser was too big. Square root of u. All right, 1 to 10. Okay, so pi over 18 times 2/3, 10 to the power 3 over 2 minus 1. When we simplify, this is going to be 3.563. Okay, next example. Again, the surface area of revolution is surface area is equal to 1 to 3, 2 pi times the radius times the arc length, which is 1 to 3, 2 pi times the radius times square root of 1 plus f prime of x squared dx. So I'm given f of x is given to me. F of x is 2 root x. And if I find f prime of x, that would be 2 times 1 over 2 root x, which is just 1 over root x. And f prime of x squared would be 1 over x, because if I square both sides, it's just 1 over x. All right, so let's go ahead and plug in. Surface area of solid is 1 to 3, 2 pi. What's the radius at any given point? The radius would be the y value. We want it in terms of x. And inside the square root, we have 1 over 1 plus x dx. Let's go ahead and evaluate that square root. I can pull out a 4 pi outside. 1 to 3. We have square root of x. And inside, we can try to write it as a single fraction inside the square root. And that is 4 pi 1 to 3 square root of x times 1 plus root x over root x dx. Okay, looks like we can cancel the root x and root x, which is 4 pi 1 to 3 integral of 1 plus x dx. We can use a u substitution here because the derivative of 1 plus x is sitting outside. I can just treat it as a u. 1 plus x to the power 3 halves multiplied by 2/3, and the bounds are 1 to 3. It is time to, sorry, it's not 4x in the front, it's 4 pi in the front. Okay, 4 pi almost looked like an x. Okay, it's time to go ahead and plug the upper bound and the lower bound in, and it turns out to be 8 pi over 3, 1 plus x from 1 to 3, which turns out to be, plug the bound 3 in first, which is 8 pi over 3 times 8 pi over 3 times 4 minus 8 pi over 3 times 2. And that's going to be 16 to power 3 halves. Oh, there's a power 3 half as well. Okay, ignore that. I totally dropped the power 3 halves there. So let me clean this up, get some more room for myself here, and we can work it out there. So let's go ahead and plug the upper bound in and the lower bound in. 4 pi times 2 over 3, and then we have 1 plus x to the power 3 halves. The bounds are 1 to 3. Okay, that's 8 pi over 3. If I plug the 3 in there, that's 4 to the power 3 halves minus 2 to the power 3 halves. Okay, which is 8 pi over 3. Square root of 4 is 2. 2 to the third power is 8 minus, this would be just 2 to the third power square root of 8. And we can simplify it a little more. I think we can pull out a 2 from inside if we want. This is 2 times 4. This is 2 root 2. I would just leave it at that point. I could pull the 2 out in the front, 16 pi over 3, and then 4 minus root 2 inside. The 37 is just the page number. Ignore that 37. Okay, 4 minus root 2, 16 pi over 3 is my surface area of the solid in this case. Okay, let's look at a couple more examples. Find the exact area of surface obtained by rotating the given curve about x-axis. So we are rotating this curve about x-axis. Again, to find the surface area, we need the 0 to 1, 2 pi times the radius. Radius will be the y value at each point. 1 plus square root of e to the power x. 1 plus, I should find the derivative first because I need to plug it in. Y is equal to square root of 1 plus e to the power x. I can write as 1 plus e to the power x to the power 1 half. Y prime would be 1 half 1 plus e to the power x to the power negative 1 half. Okay, which turns out to be, we must multiply with the derivative of the inner function because of the chain rule. So it turns out to be e to the power x over 2, and then square root of 1 plus e to the power x. This is my y prime. And we're going to plug it in and square it. So e to the power x over 2 root 1 plus e to the power x squared dx. All right, so surface area is 0 to 1, 2 pi, square root of 1 plus e to the power x. And then square root of 1. Let's do some simplification inside because it looks a little bit tricky and messy inside. I could pull the 2 pi outside. I would do it in the next step. Okay, so if I square this, this turns out to be e to the power 2x divided by 4 times 1 plus e to the power x dx. Okay, from 0 to 1, 2 pi can be pulled out, 1 plus e to the power x. Now let's get the common denominator inside. The common denominator looks like 4 times 1 plus e to the power x. The first fraction will get multiplied, top and bottom, with 4 times 1 plus e to the power x, 4 times 1 plus e to the power x. So it's 4 plus 4 e to the power x plus e to the power 2x dx. Let's see, I'm gonna get myself a little more room here, and where should we go from here? 0 to 1, 2 pi is pulled out, square root of 1 plus e to the power 2x. I have a square root of 4 in the denominator, so I'm going to pull out the 2 outside, and I'm going to isolate the top and bottom here. Okay, I got the same thing in the numerator, same thing in the denominator. That is gone. The 2 and 2 is gone. So I'm left with pi 0 to 1. Inside, it looks like it's a perfect square to me. If I do e to the power x plus 2, if I square it, I should be able to get that back. So e to the power x plus 2 squared should be giving me, if I FOIL it, I should come up with that. That's perfect. Now we are ready to cancel between the 2 and the square root. So we're left with pi and the integral of 0 to 1 e to the power x plus 2 dx. This integral is not bad because integral of e to the power x is e to the power x plus 2x, and the bounds are 0 to 1. Turns out to be, let's go ahead and plug the bounds in. Pi is outside, e to the first power is just e plus 2 minus e to the 0 power is 1. And that turns out to be pi times e plus 1. Looks like that should be my final answer. So that's the surface area of the solid of revolution that we just did. Okay. All right. This is a try me problem. Go ahead, pause for a minute, try the problem, come back and check with me. Okay. Again, when y is a function of x and we're revolving around the x-axis, the surface area can be expressed as 2 pi a to b f of x square root of 1 plus f prime of x squared dx. So I'm given the y here. I want to find out y prime. I guess finding the y prime, I probably have to use quotient rule, or I can separate the two fractions. Let's go ahead and try it. Y is x to the 6th over 8x squared plus 2 over 8x squared. Okay, it turns out to be 1 over 8. No. It would be x to the 4th, 1/8. 1 over 8x to the 4th and plus 1 over 4x to the power negative 2. So now I wrote it in terms of exponents and I have negative exponents. Finding the derivative, it's not too much work. 4x to the 3rd plus 1/4 times negative 2x to the power negative 3. Okay, that turns out to be 1/2 x to the 3rd minus 1 over 2x to the 3rd. All right. Good. So we found the derivative. Remember, we also have to square it when we plug it into the formula. So let's go ahead and plug it in. Surface area would be, let's pull out the 2 pi outside. We're going from 1 to 3. F of x is x to the 6 plus 2 over 8x squared. That's my y value at any given point. Maybe I should just write it in terms of simplified, which is 1 over 8x to the 4th plus 1 over 4x to the power negative 2. F of x square root of 1 plus f prime of x squared dx. Okay, I could have pulled the 1/2 out of my square. It might make my life a little easier. Or I can just continue working with that at the same spot where it is. So let's go ahead and foil inside. Foil the parentheses, open the bag. That is going to turn out to be 1 plus x to the 6 over 4 minus 2x to the third over x to the third plus 1 over 4 x to the 6 dx. Okay, looks like the x to the third and x to the third is gone here. So 2 pi 1 to 3 1/8 x to the fourth plus 1/4 x to the negative half square root of 1 plus x to the 6th over 4 minus 2 plus 1 over 4x to the 6th dx. Okay, 1 and 1 minus 2, this would be 1 minus 2 is negative 1. Let's see, would it be 2 times 1/2 times negative 1/2? Let me write the whole thing here when I foil. Just want to double check my work for foiling. 2 times 1/2 x to the third times 1 over 2x to the third. Okay, so 2 and 2 is gone. X to the third and x to the third is gone. I would be left with 1/2 here. So this would be 1/2. This is 1/2. Okay, 1 minus half. These are the like terms, so I'm going to combine them next. 2 pi 1 to 3 1 over 8 x to the fourth plus 1 over 4 x to the negative 2. And then inside the square root, 1 minus half turns out to be a positive half plus 1 over 4x to the power 6th. Okay, let us see. So it looks like inside I do have a perfect square. So 2 pi 1 to 3 1 over 8 x to the fourth plus 1 over 4 x to the power negative 2. And we have a perfect square, which is x cubed. I have 1/4 here. I can probably pull that 1/4. So that is x cubed over 2. X cubed over 2. Could I pull a 1/4 out of the square root? What happens if I pull a 1/4 out of the square root? I think that might help me. If I pull out 1/4 out of the square root, let's do that. It might make my life a little bit more simpler if I pull a 1/4 out of the square root. If I pull a 1/4 out, this would be x to the 6th plus 2 plus 1 over x to the 6th dx. When I'm going to multiply with 4, I will have 1/2 back. That looks good. So we can pull out the 2 out in the front because square root of 1/4 is 1/2. So I'm writing it all the way in the front. And I could actually pull out 1/4 from here as well. Maybe I'll do that in the next step. So inside looks like I do have a perfect square, which is x cubed plus 1 over x cubed squared. Let's go ahead and check by foiling if that is going to give me the parentheses back. X cubed plus 1 over x to the third squared will give me x to the 6th power plus 1 over x to the 6th power plus 2 times x cubed times 1 over x cubed, which is what I have in my parentheses. Okay, so at this point, it is okay to go ahead and cancel the 2 and 2 and here as well. So I have 1/3 1 over 8 x to the fourth plus 1 over 4 x to the power negative 2 times x to the third plus 1 over x to the third dx. So what I recommend doing at this point is foil, a lot of algebraic simplification. You're gonna have to distribute. So here, 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 and combine the like terms. And after doing that simplification, it's going to turn out to be 1, 2, 3, x to the 7 over 16. Okay, let us see. So there's a 2 pi over here. Not enough room. Let's go ahead and try to distribute these and see what do we come up with and combine the like terms. Okay, so 1, 2, 3, 1/8 x to the 4th times x to the 3rd is 1/8. There is still pi in the front. Do not drop that pi. 1/8 x to the 7th power plus 1/8 x plus 1/4. 3 plus -2 is just 1x, and then plus 1/4 x to the 5th in the denominator. Okay, we still have dx. Okay, so combine the like terms, go ahead and do the integral here and find out what does the integral turn out to be. I'm going to leave it at this point. So this point is just simplifying the definite integral, and I'm running out of the space. So I'll leave that fun problem for you guys. Okay, the next problem for the surface area of the solid is, okay, the curved surface of a funnel is generated by revolving this curve over x-axis from the interval 1 to 2. Approximately how much paint, so we're looking for volume of the paint needed if you want to cover outside of the funnel with 0.05 centimeter thick layer of paint. Okay, so first of all, f of x is given to me x cubed plus 1 over 12x. And we want to find f prime of x. That would be 3x squared minus 1 over 12x squared. So surface area is going to be 2 pi going from 1 to 2. 2 pi, 1 to 2. Radius, which is x cubed plus 1 over 12x. And 1 plus f prime of x squared dx. Okay, here we are. Now, again, FOIL, combine the like terms and see if you end up with a perfect square inside, which you do sometimes. So 2 pi 1 to 2 x cubed plus 1 over 12x. I'm going to FOIL, open up this bag. 3x squared turns into, so this would be 9x to the 4th, 9x to the 4th, plus 1 over 144 x to the 4th, x to the 4th minus 2 times 3x squared times 1 over 12x squared. Okay, surface area is equal to 2 pi 1 to 2 x to the 3rd. We cannot do anything with the outside terms until we simplify the inside as well. So let's see if there's anything I can get rid of. The x squared and x squared I can get rid of. 2 and 6 here. So that would become 1/2, negative 1/2, because I have 6 on the top, 12 on the bottom. So it turns out to be 1 plus 9x to the 4th plus 1 over 44 x to the 4th minus 1/2 dx. Again, like terms here, 1 minus half will be positive 1/2. Surface area is 2 pi 1 to 2 x cubed plus 1 over 12x. Square root 1 minus half is positive half. plus 1 over 144x to the fourth dx. Inside, if you look carefully, this is a perfect square. So surface area is 2 pi 1 to 2. We have to keep writing everything as it is until our inside is simplified. That is a perfect square, 3x squared plus 1 over 12x squared to the second power dx. Now, cancel the square and the square root. Square and square root can be cancelled. Again, we have to FOIL now. 2 pi 1 to 2 x to the third plus 1 over 12x times 3x squared plus 1 over 12x squared dx. No square root anymore, so all I have to do is FOIL, combine any like terms, and then do the integration. So for the FOILing, x cubed times 3x squared is 3x to the fifth. When I multiply these, I would have plus 1 over 12, or x over 12, because I have x to the third on the top, plus I would have 1x on the top, x over 4, plus 1 over 144 x to the third dx. Okay, at this point, you can do it manually or you can plug it into your calculator. I did go ahead and plug it into my calculator. You can actually do that without simplifying, but if you don't have a calculator, then all you are left with is you have to do integration, individual pieces, integral of pieces. What's going to be the integral of 3x to the fifth? It would be 3x to the sixth over 6. And integral of, it would be 1 over 12 times x squared over 2 plus 1 over 4 times x squared over 2 plus 1 over 144 times x to the power negative 3 plus 1 is negative 2. We're also going to divide it with negative 2, which would be, so divide with negative 2 here. That would make 144 negative. So I'm going to write it as negative 2 times 144. My bounds are from 1 to 2. As you can see, there's a lot of plugging in upper bound, subtracting the lower bound. Your answer should come out to be 12289 pi over 192. It's very nice to leave these in terms of, this would be the surface area. And let us see if we're given, we're not given any units, but it's very good to leave them in terms of exact values than trying to find the decimal approximation. Okay, we wanted to find the volume of the paint here. So volume of the paint would be actually how much volume of the paint is needed. It did say in the problem we wanted to have 0.05 centimeter thick layer of paint. So we would do surface area times the 12289 pi over 192 times 0.05. However thick layer do we want? It would be 10.1 centimeter cube is going to be the volume of the paint we need to cover this solid of revolution. Okay, all right, couple more examples. We have Gabriel's horn. We will come back to this when we talk about improper integrals, so I'm going to skip the Gabriel's horn for now, because in order to understand it, we need to have knowledge of improper integrals. We haven't covered them yet. Okay, there's a try me problem. Only set up the integral, don't evaluate the integral. So we want to find the surface area of solid of revolution. So surface area is going from 0 to 1, 2 pi, the radius is x to the third, and then 1 plus f prime of x. F prime of x would be 3x squared dx. Okay. Again, I did not ask you to simplify, but if you did go ahead, you could write it as 1 plus 9x to the fourth dx. We did this problem earlier, so you can go back and check in detail if you need to. When you use the u substitution here, so we're going to use use substitution here, and your answer should come out to be 3.563. I believe this was the very first problem we started with, we tried. Okay, here's the next problem. Find the area of the surface formed by revolving the graph of f of x equals x squared on the interval 0 to root 2 about the y-axis as shown in the right, shown at the right. Okay, so we can actually do it in two different ways because we are revolving about the y-axis. You still have f of x, you still have y as a function of x. So it's up to you, how do you want to express it. So method 1, we can leave it as y as a function of x. When you think about the radius of your band, radius would be the x value. Surface area, y as a function of x. So surface area in that case is going to be 0 to 2. The x is root 2. 0 to root 2. 2 pi, the radius will be the x value, and 1 plus f prime of x squared dx. So if f of x is x squared, f prime of x is 2x. So which would be 0 to root 2, 2 pi x square root of 1 plus 4x squared dx. Okay, that's one way of handling this problem. Now, you could also go ahead and express this one as you could express x as a function of y. So you could say x as square root of y here. In that case, for your surface area, so what's going to be the integral here? So that would be dx dy. It was going to be 1/2 y to the power negative 1/2. Okay, so surface area in that case would be, the bounds will be the y values in that case, which are from 0 to 2, 2 pi. The radius is the difference between the axis of rotation. How far is the distance from the axis of rotation, which is the x value, but we would like it in terms of y in that case, because we're expressing our integral in terms of y. We used x as a function of y, and then square root 1 plus f prime of x, which is 1/2 y to the power negative 1/2 squared dy. Either way, go ahead and evaluate the integral, simplify, should come out to be 13.614, approximately equal to 13.614. Okay, and that's the end of surface area of a solid of revolution. Again, just to review really quick, remember, if y is a function of x and you're rotating about the x-axis, this formula would be used. If you're rotating about the y-axis, this formula would be used, because basically your radius is your distance from the axis of rotation to the curve. And if you're given x as a function of y, then this formula would be used. Okay,